In this video, I will discuss the derivation of time-independent Schrodinger wave equation by a very simple method. So let's start the derivation of this time-independent Schrodinger wave equation by writing the wave function of a particle, which can be written as psi is equal to a exponential minus iota over h bar times et minus px. Now this wave function can be written in two different forms, which can be a exponential iota px divided by h bar and exponential minus iota et divided by h bar, or we can write this wave function as psi is equal to phi exponential minus iota et divided by h bar, where we separated this position dependent part of the wave function from this time dependent part, and this position dependent part of the wave function is phi. Now writing the time dependent Schrodinger wave equation, which is E psi is equal to h psi, where h is the Hamiltonian operator, which generally can be written as minus h bar square over 2m d square over dx square plus u. This is the general form of a Hamiltonian operator for a particle moving in one dimension. So this is our time dependent Schrodinger wave equation. Now in the next step, we will put the value of our original wave function psi on both sides, and we have the following equation, which is E phi exponential minus iota et divided by h bar is equal to minus h bar square over 2m d square over dx square plus u time phi exponential minus iota et divided by h bar. As in the Hamiltonian operator, we have only the second order derivative with respect to position, so this will not affect this time dependent part of the wave function. So this will be cancelled out on both sides, and we are left with E phi is equal to minus h bar square over 2m d square phi over dx square plus u phi, or this can be written as E minus u phi is equal to minus h bar square over 2m d square phi over dx square, or we can simply write it in this form as d square phi over dx square plus 2m divided by h bar square E minus u phi is equal to 0. This is our final form of time independent Schrodinger wave equation. This is also known as the steady state form of the Schrodinger wave equation. This is said to be steady state because there is no evolution of wave function with respect to time. So I hope now you have a clear understanding of the derivation of this form of Schrodinger wave equation. Kindly subscribe this channel for more physics and mathematics videos and concepts.